back to hellgeekarena, and today we are back with another very interesting problem on Leetcode, which is the number complement. Now, if you see that this problem has been tagged as an easy problem, and I do agree with it because it has a very easy and a very simple kind of a solution along with it. So why I want to touch this problem is because it kind of this problem kind of covers a very basic and very important few of the concepts related to bitwise operations, which would be very useful when you go on and touch some of the very hard problems related to bitwise operations. So let's start going through this problem. So it says that the complement of an integer is an integer which you get when you flip all the zeros to ones and all the ones to zeros in its binary representation. So here it gives an example where the binary representation of 5 is 101, and the complement that you get after converting ones to zeros and zeros to 1 is basically 0 1 0, which is basically the binary representation of 2. So the decimal number which was input is 5, and the complement binary representation is 1 0, which is like the binary representation of the decimal number 2. So you have been given basically a decimal number, you have to find its number complement. So let's see how we can do it. So we are going to discuss two possible solution for this problem. Let's view the first one. So in the first solution, like, we are going to do exactly what the problem statements say. That is, first we are going to convert the number to its binary representation. Then we will replace all the ones with zeros and zeros with ones in its binary representation, and then we are going to convert back the binary representation to decimal representation. That is, if we take the prior example, we will first convert 5 into 101, and in the next step we are going to replace its zeros with ones and ones with zeros. That's when we are going to get 0 1 0, and then we are going to convert back that 0 1 0 into a decimal representation, which is 2. So let's take some examples and let's see how we can do this. So let's take a few of the examples and see how first of all we can convert a decimal number into its binary representation. So let's start with 5. So how we do it is basically we will continuously keep on dividing it by 2 and keep on saving its remainder. So we divide 5 by 2, we get 2, remainder is 1. Then we again divide 2 by 2, remainder is 0. And again we divide 1 by 2, remainder is 1. So we see over here the binary representation is 1 0 and 1. So 1 0 1. Let's try another number, let's say 9. So 9, again we divide by 2, we get 4 over here, remainder is 1. Then again we divide 4 by 2, we get 2 over here, remainder is 0. Then again this, and yeah, so we get like 1 0 0 1 over here, right? So we just keep the remainders in reverse order and we put it over here. 1 goes here, 0 goes here, again 0 goes here, and 1 goes here. So yeah, this is how we convert the numbers into their binary representation. Now the next ask was that we do if you see the step 2, it was basically replacing all the zeros with ones and ones with zeros. So let's do it one by one. So for 5 we got like 1 0 1. So when we convert ones to zeros and zeros to 1, we get 0 1 0. And similarly for 9, we got 1 0 0 1, and we convert ones to zeros and zeros to 1, we get like 0 1 1 0, right? So basically this is kind of the what we have got till now is basically a binary representation of complement of these numbers, right, which were originally given to us. So we move to the third step, which is basically converting the binary representations back to the decimal representations. So how do we do the reverse thing, that is conversion of binary to decimal? We kind of maintain the indexes of the individual binary digits, like this is 2, this is 1, this is 0, and then similarly this is 3 2 1 0. So then we kind of multiply by the powers of the 2. So 2 raised to the power 2 multiplied by 0, that is 2 raised to the power index of 2, and then multiplied by the digit present over here, plus 2 raised to the power 1 multiplied by the digit present over here, and then similarly 2 raised to power 0 multiplied by the digit present over here, which is 0. So this takes us to 0 plus 2 plus 0, which is again equivalent to 2. So what we get from this is like the complement of 5 is 2. Basically, for what we did was, first we tried to find the binary representation of 5, which was 101. Then we just converted ones to zeros, zeros to 1, which is like 0 1 0, and then what we did was we just converted back 0 1 0 back to its decimal format by multiplying by the indexed powers of 2. So 2 raised to power 2 into 0 plus 2 raised to power 1 into 1 plus 2 raised to power 0 into 0, which takes us to 2. Now similarly, let's try it for 9 in the similar way. We are going to do is 2 raised to power 3 multiplied by 0 plus 2 raised to the power 2 multiplied by 1 plus 2 raised to power 1 multiplied by 1 plus 2 raised to power 0 multiplied by 0, which takes us to 0 plus 4 plus 2 plus 0, which is like 6, and like basically 6 will be our answer for 9's complement. So it's exactly the same way we can we did it for 5, we can do it for 9, and similarly we can do it for any other number. So basically this is one possible solution we can opt for. We can easily code this solution. All we need to we just need to follow this simple algorithm to solve this problem. But before we jump into the coding this solution, I would like to discuss another possible solution, another one tricky solution, but which is much easier to code. Now before we jump into this solution, let's discuss about another very important concept in bitwise operation, which is XOR. So what XOR says is that let's say we want to find the XOR of two numbers, which is let's say 5 and 9. How we find the XOR is basically we represent it by their binary representation. Like we already saw that the binary representation of 5 is 101, and we saw that the binary representation of 9 is basically 1001. So how we find the XOR of it is basically whenever the two digits that we see over and above each other which are same, we put 0 over there, and whenever we see two digits which are like different, we put 1 over there. So if we see like 1 and 1, they are same, so we put 0 over here. 0 and 0, these are also same, we put 0 over here, and 0 and 1, these are different, so we put 1 over here, right? So this is how we calculate the XOR. And then again, like we did before, we can easily convert it into decimal format, right? So what we are going to do is 2 raised to power 3 multiplied by 1 plus 2 raised to power 2 multiplied by 1 plus 2 raised to power 1 multiplied by 0 plus 2 raised to power 0 multiplied by 0, which takes us to 8 plus 4 plus 0 plus 0, which is like 8 plus 4 is equal to 12. So basically XOR of 5 and 9 becomes 12. So this is how we find XOR of two numbers. Now there is one very interesting property about XOR is that whenever we take the XOR of any of the digits with 1, right, it automatically that reverses the digit. Like if we take XOR of 1 with 1, we are going to get 0. And if we take XOR of 1 with 0, we are going to get 1 over here. So if you see, it maps 1 to 0 and it maps 0 to 1. So if we have a binary representation of a number, right, and we take XOR of it with all the ones, right, so what it should do is basically reverse all those digits. Like we take XOR of 1 with 1, it gives us 1. 0 with 1, it gives us basically 1, and we take 1 with 1, it will give us 0. So basically what it is doing is that if we do a XOR of a number with all the ones, we are going to get our desired complement of that number, basically, because 1 has the property that whenever you take a XOR of 1 with any other digit, it will always give you the reverse of that digit. So basically we can utilize this property to find the XOR of the number. So let's look at this algorithm. How we can do this is basically find the number of digits in the given number. Find the number s is equal to 2 raised to power x minus 1. Now why we talk about 2 raised to power x minus 1? Let's say 5 has had like 3 digits in 3 binary digits with it. So 2 raised to power 3 minus 1, which takes us to 2 raised to power 3 is 8 minus 1, which is 7. So we get 7 over here, right? And what is 7? What is the binary representation of 7? It is 1 and again 1. So basically it is 1 1 1, which is basically the combination of ones we need for finding the complement in case of a 3-digit number, 3-digit binary number basically. So that's why what we are going to do is that we are going to find a number which is 2 raised to power x minus 1. Then what we are going to do is basically find s XOR n, where s is the number 2 raised to power x minus 1, and XOR, and basically n was the original number given to you. So basically what we need to do is find 5 XOR 7, which will give us 2, which is the intended answer for us. Now let's take a look at the code for this solution. So in the solution over here, we are just going to represent the 3 steps that we just discussed in the form of a code. So the first step was basically counting the number of binary digits that are there in the number. So we already saw, like when we were converting 5 and 9 into their corresponding binary representation, we continuously kept on dividing them by 2 and maintaining the remainder. So what we need to do over here, we don't need the remainders for us. What we just need is basically the digit count. So we'll keep on dividing the number by 2 and incrementing the digit count by 1 till the point the number doesn't reach 0. So we'll keep on doing that, and at the end of the day, the dig variable is going to have the number of binary digits that are there in the number. So in case of 5, after running till this point, we are going to have dig value equivalent to 3. So now the next step was finding 2 raised to the power x minus 1. So for that, what we are going to do is that basically we are going to do a math.pow of 2 comma digit minus 1, which is going to give us the required number with which we should take the XOR of the given number. So in case of 5, what will happen is that digit count is 3, so 2 raised to the power 3, which gives us 8 minus 1 is 7. So math.pow minus 1 over here is going to give us 7, and then we are going to take a number XOR with this number. So 5 XOR 7, so this will return us 2 as the answer, which we can see over here. So basically, this is basically an accepted solution on Leetcode for this problem. And thanks for watching this video. Thank you.